Let us see losses in transformer. So there are two losses occurring in transformer, which are core loss, also known as magnetic loss, constant loss, or iron loss. The second is copper loss, also known as ohmic loss, I square R loss, variable loss, resistive loss. So about core loss, core loss are further subdivided as hysteresis loss, and eddy current loss. Right. Let us see hysteresis loss. So this loss is occurring due to magnetic reversal. Magnetic reversal in the core, right? And this loss can be reduced by using CRGO, that is cold rolled grain oriented silicon steel as core material. Silicon steel as core material, right, with high permeability. The loss can be given as hysteresis loss PH equal to KH Bm power eta F to V watt, where KH is constant of proportionality, Bm it is flux density, maximum value, eta is Steinmetz constant, and its value is ranging from 1.5 to 2.5. Typical value is 1.6. F is supply frequency, and V is volume of core. Right. If I rewrite pH, so you can see this is constant and volume of core is also constant for a design, transformer. So I can write PH is directly proportional to Bm power 1.6 if I take typical value as 1.6 into F. We know EMF equation of transformer E equal to 4.44 F phi m into N1 or N2, or I can write V, E is represented as V, and it can be written as V is directly proportional to F phi m, or I can rewrite phi m is directly proportional to V by F, right? So I can rewrite this Bm as Bm is flux density. It can be written as phi by A. We know Bm is phi m by A, or Bm is directly proportional to phi m because A is area of core, which is constant. So I can write it here as it is directly proportional to phi m power 1.6 into F, and if I replace phi m here, it will be V by F power 1.6 into F. For constant frequency will be constant, and hysteresis loss will be written as, or will be shown like this. That is, hysteresis loss depends on mind you, this is voltage, not volume, right? This is here, you can see voltage. Coming to second loss, that is what? Eddy current loss. Eddy current loss. So we know as transformer core is under influence of alternating flux. So due to this, an EMF will induce in core. EMF will induce in core, right? And this EMF will cause circulating current at the surface of core. Circulating current, that is eddy current at core surface. So this current, which is eddy current, will cause, this will result, it will result eddy current loss. Eddy current loss. This loss can be minimized by increasing resistivity of core. Loss can be reduced by increasing resistivity of core and by increasing length of eddy current, circulating current, right? Eddy current. So resistivity can be increased. Resistivity can be increased by adding small amount of silicon by adding small amount of silicon, that is 3 to 4%, not more than that. If you add silicon more than that, the material will be brittle and it will shatter like a glass. And length of core can be increased by laminating. Laminating core will increase length of eddy current. The lamination thickness will be thickness of lamination is ranging from 0.3 to 5 mm for transformers which are used in power system, and for electronic circuitry it can be 0.01 mm to 0.2 mm. Right. Eddy current loss is given by PE equal to KE Bm square F square T square V watt, where Bm is same, that is flux density, F is supply frequency, V is volume of core, T it is thickness of lamination. Thickness of lamination. So I can rewrite PE is directly proportional to, as we know, K is constant, the supply thickness of given transformer lamination will be constant, volume will be constant. So I can rewrite this as Bm square F square, and we know Bm can be replaced by phi and phi can be replaced by V by F. So by that I can replace it V by F whole square into F square, or eddy current loss is directly proportional to V, where V is what? Voltage. So we can say that eddy current loss and hysteresis loss both are voltage dependent. Next loss, that is variable loss. Variable loss, that is copper loss. This loss is due to winding resistance, and it can be given as PCU copper loss equal to I1 square R1 primary winding copper loss plus I2 square R2, or if we have referred circuit on any side, I can write I1 square RE1 or I2 square RE2. We know RE1 and RE2. They are the equivalent resistance referred on primary side and equivalent resistance referred on secondary side. So copper loss, I can say it is directly proportional to I square, and it depends on current value, right? So based on this we can go for transformer rating. While transferring power, there occur copper loss. Copper loss and core loss in transformer, right? And which appear in form of heat, right? So this heat developed in transformer, must be below certain value, certain value to protect insulation, right? Protect insulation. So as these losses are dependent on voltage and current, as these losses are dependent on voltage and current, therefore transformer rating is given as given as product of voltage and current. So we can say transformer rating equal to VR, that can be written as volt into ampere, that is VA, or can also be written as kVA, kilovolt ampere. And we can write, we know V1 I1 equal to V2 I2. This is what volt ampere rating. And if I divide them by 1000, V1 I1 by 1000 equal to V2 I2 by 1000, it will be kVA. So this is what rating of transformer, which will be decided by the temperature rise. That's all for this lecture.